Okay, good morning, ladies and gentlemen. Uh, my name is Arjun. I'm the Senior Vice President for Technology Development, and I was asked not to be technical. So I'll try my best. Okay. So today, my talk, I'm going to talk about CMOS to MTM manufacturing. MTM stands for more than more. So I'll explain to you some of this very shortly. So first, for those who do not know what exactly SilTerra is actually a 200 or 8-inch fab. We are basically having a capacity of around 40,000 wafer starts per month. And we have around 122,000 square feet of class 100 clean room, whereby all these wafers are manufactured. And one of the key things is late last year we got this automotive certification, which is the IATF certification. And for the last 4+ years, we have been focusing on transiting from traditional CMOS to more than more technologies. So what we exactly do, though a lot of people ask me, are you wafer guys? Yeah, we are wafer guys, but we don't manufacture raw wafers. Okay, we actually buy the raw wafers from suppliers like MEMC, for example. Okay, and then we use our own process technologies, and we loosely call them as CMOS process technologies to fabricate these wafers. And this is how a fully processed wafer looks. All these patterns you see are actually the so-called ICs or chips. Industry uses both the words. What we ship to our customers is in this form. Okay, this processing takes around 60 days. Okay, it's a very quite complex process. And our customers, they will singulate them into what is called as a die. This is one chip. This is what goes into the electronic devices. And then they use other supply chains to basically package them. Okay, this is what you see on your PCBs. Okay, this is a very simple of what we do. So our whole business is over here. Okay, that's why we are called a foundry, because we don't have an end product. Okay. So now I'm going to talk about Moore's law very quickly. Very simple way to explain Moore's law is that this is what is called as a technology node. The way to describe this is, the idea is to print smaller lines. If you have the ability to print smaller lines, the transistors will become smaller. So in a given silicon, you can actually have more transistors. So one of the good things about this technology is that as you make the technology node smaller and smaller, this is in nanometers. Okay. One of the important thing is the processing power goes up significantly higher. So there is a need for the transistors to become smaller and smaller, because you will have higher and higher computing power. Okay. So, however, you cannot run all these technologies in one single factory. Okay. There is a segregation, and that segregation is, it happens around at 90 nanometers. Below this, there are other technologies also, I didn't add that. Below this is all manufactured on 200 or 8-inch. That means the diameter of the wafer is 8-inch or 200 And this is where exactly SilTerra is. For the advanced nodes, you need to have what is called as a 300 or 12-inch fabs. Now here it's just an arbitrary scale, just to describe this thing, so please don't read into the numbers. Okay. And this technology node is typically used to manufacture your mobile phone application processors, your high power computing, your memories, the so-called gigabytes and the terabytes of memories. They all come from 300 And trust me, if this technology was not there, the smartphones would not be in your hands. What you would be using will be those Nokia future phones. The reason the computing power on the smartphones is so tremendously high is because these. Okay. So in 2000, early 2000, this transition started. The industry before 2000 was all 200 mm. Then in the early 2000, the transition started to 300 mm. At that time, all the analysts have predicted that all the technologies will move to 300 mm and 200 mm will become absolute. But fortunately, that didn't happen. Okay? The reason that didn't happen is because on the 200 mm fab, we still manufacture all these other chips. Because in order to build a smartphone, you just don't need an application processor and a memories. You also need all those chips, which is the power management chip, the touch screen controller, all this. So with this combination, the 8-inch or the 200 mm fabs also started enjoying a robust demand. And now the industry believes that both 200 mm and 300 mm have to coexist in order to serve the electronic industry, right? So this is all about Moore's law. So if anybody says they're following Moore's law, that means they're primarily migrating from 200 mm to 300 mm. The next one is going to be 450 mm. Okay? However, for a fab like SilTerra, what can we do, right? And here, as I said, we cannot go in this direction. We need a 300 mm fab. So the way we are doing is that we are actually adding additional functionality to the CMOS technologies that we already have, right? And for example, these additional functionalities is power, MEMS, photonics, and bioscience. If we stay here, we will become irrelevant. We need to reinvent ourselves in order to add this functionality. And adding this functionality is not easy. Okay? So if you look at the emerging markets, so-called, all of us know about IoT, data centers, primarily with 5G, it's coming back into focus, artificial intelligence and machine learning, autonomous cars, healthcare, point of care testing. All these are actually creating new opportunities for 8-inch fabs. Okay? But again, as I said, we need to reinvent ourselves. So that's where the so-called more than more technologies come. And the best way to describe this is that these are the traditional technologies of SilTerra, so-called CMOS technologies. Now we need to move to what is called as more than more technologies. So in this more than more technologies, we have developed a process called IoT. This is primarily for IoT applications. It's an ultra-low power process. We have power technologies. I'm going to talk about this later. We have silicon photonics. We have MEMS. And then we have life science. So you can say, what's the big deal here, right? So let me explain a very simple way why these are so complex. One of the common element you see in all these technologies, including this, all the way to here, the domain is electrical. Your input signal is electrical, your output signal is electrical, right? All these chips are basically electrical driven. However, when I go to photonics, the domain changes to optical, right? Either the input or the output is now is now optical, right? It's not electrical anymore. And when you come to MEMS, it's mechanical, because actually in the MEMS, the EMS stands for electromechanical system. The M is micro because it's at a micro level. It's mechanical, the output. Okay. Next one, life sciences, is biology. So you can imagine how challenging it is for a fab that has been, not just for the fab, but for the industry that has been running electrical domain since the very first transistor was invented, and now we have to change. We have to have all these new domains coming into the picture, right? So for a fab engineer, the worst thing that can happen is that what is non-critical here becomes critical here. That's the worst nightmare, right? Because you need to then identify what those are and tend to work on them. Okay? So in the interest of time, I'm not going to talk about all of them, but I will give you some examples later. So one of the next thing to do is to map them to the end markets. So these are the 5 MTMs I talked about, right? More than more technologies. These are the various end markets, right? So if you map them, for example, if you take the IoT, it basically serves the IoT applications. If you take the power, it has the ability to serve both the autonomous cars and the data centers. If you take MEMS, it actually serves 4 of them. And the reason MEMS does is that MEMS is one of the technologies that is used to manufacture sensors. Okay? So 2 great examples from MEMS is actually the gyroscope and accelerometers in your phone, right? The gyroscope and accelerometer sensors are used to calculate your GPS coordinates. So if the MEMS technology was not there, Grab and Uber would not be here. Because without the GPS coordination, there is no way they're going to work. And the worst thing in this technology MEMS is, if you actually look at the semiconductor industry, it's been very successful and it's been very reliable. The reason for that is, when these computations are done or when these calculations are done, nothing moves. Mechanically, nothing moves. Yeah, you can argue electrons move, but that is electrostatic motion. It's not mechanical. But here, things will start moving. So that's a big change for the industry. Yeah. Then if you look at photonics, photonics plays a very important role for data centers because it has the ability to boost up the speeds and reduce the power consumption, which is extremely important for 5G. Okay? And then life sciences, of course, it directly serves the healthcare market. Okay? So now I will talk about, as I said, in the interest of time, I'll talk about few technologies. First is power. I think all of you guys remember, right? 15 years back, probably, if you have to get into your car, you have to manually unlock, open the door, get in, insert the key into the ignition, start the engine and start driving, right? But today, you just walk into your car, you just need to have your key in your pocket, you can walk in, press the button and start driving. Well, if it's an autonomous vehicle, you won't be driving, right? So how is that possible? Main reason is the electronic content in present day cars, right? They're totally everything in your car, including the power doors, the power windows, the safety, chassis, is actually controlled by electronics. Because of this electronic content, all the automotive industry is actually enjoying a very robust growth for the last 5 years. Okay? However, if you think this is very good, wait till autonomous cars come in. Autonomous cars, in addition to what I showed in the earlier chart, you need to have LiDARs, sensors, GPS, onboard computing, video cameras. So you can imagine how significant the electronic content in the cars are going to go up. So in order to address this market, we developed the power management platform, bunch of technologies that can serve these markets. And in addition, you can also use these technologies to manufacture in solar inverters, UPS, EV charging, motor drivers. These are some power MOSFETs. So what we did is that we used our high voltage expertise and we came out with a BCD technology that can be used for any of these markets: wireless chargers, DC to DC converters, load switches, and then power MOSFET primarily for autonomous vehicles, data centers, renewable energy. The most important thing is the IATF certification. That's our ticket to the automotive industry, right? So with these technologies, we can actually address all the automotive related applications. I would say most, I wouldn't say all. Next one is smart headlights. So what do you guys see here? Quite futuristic, right? Car projecting images. Why do you need that? So use the car headlight to project images. So why do you need that? If you're a pedestrian and you want to cross the road, you see an autonomous vehicle coming, do you think you guys will have the courage to cross? Do you know that the autonomous vehicle has detected you? Right? So I know I wouldn't. So how do you overcome this psychological barrier? So one solution is get the car to project images. So the idea is the moment the car detects you, it actually projects a zebra crossing for you. The moment you see the zebra crossing, you know the guy detected is going to stop there. All right? So it's required for autonomous vehicles. The next speaker is going to talk about this, not about this futuristic projection, but this has a very good potential. It is from the MEMS platform, and it's a highly complex product that requires us to build micro mirror components on the top of a pre-processed CMOS wafer. Okay. The feasibility is completed. The next speaker is going to talk about this. Next one is sensors. Sensors is one critical component that is needed for all those emerging markets I discussed to realize their full potential. Without sensors, they will never realize their full potential. So sensors is actually a huge topic in the industry now. Today, the industry has the ability to sense anything you want. You name it, chemical, mechanical, temperature, humidity, you can sense it. But the disadvantage with the existing sensors is they consume a lot of power, and second is they're bulky. And that does not fit into these upcoming applications, right? They need to be ultra low power and they need to be miniaturized. So one such technology we are looking is called as PMUT. It's an ultrasound transducer. This is SilTerra's own patented technology. It's a very simple way of explaining is we have a thin film membrane. So once you apply the voltage, this membrane will vibrate, and this vibrations actually creates an ultrasound. And that ultrasound generation, and this can be done at a micron level, right? And then you can have a processor underneath. So you can have your CMOS technology here and then the ultrasound transducer there. This actually offers a lot of applications. One of the most, and this is how a ultrasound transducer looks. This is one single cell. You can build them 100,000 or a million of them if you want to, okay? What is the application? Fingerprint sensors. All your phones have fingerprint sensors, right? But there's one disadvantage with that fingerprint sensor. It is a capacitive-based fingerprint sensor. So anybody can take silica gel or Play Doh, take a print of your fingerprint, and they can open it. However, this ultrasound, because ultrasound has the ability to penetrate through human tissue, it can tell you whether it's a human tissue or not. So it improves the security level, and this is very important for the banking industry. Okay, and we actually have few customers that are working with this, and in fact recently Samsung has released an ultrasound based fingerprint sensor. Okay. Next, medical applications. You say ultrasound, all the medical guys are excited because ultrasound imaging, this is a very important diagnostic tool in the medical industry. We have few customers that are signed up with us that are evaluating this. Again, the advantage with this sensor, it can be miniaturized, right? The existing ones are bulky. Second one is therapeutic ultrasound. For some of the medical procedures, you need to use ultrasound to tear the tissue. Over there, you can use this ultrasound. And the third one is biosensors. And the next one is industrial sensors, right? You can use all this with the ultrasound. So what's the key takeaway? SilTerra has a proven track record of turning proof of concept projects into mass production. One of the best examples was the DNA chip that we are actually shipping to our customers in US. And we continue to bring together the best practices of the CMOS processing into the more than more regime. And we are pushing new boundaries and allowing scalability is a core strength of SilTerra. MTM technologies play a key role in enabling mobility applications, and fabs such as SilTerra are required to embrace this change to be successful in these markets. And we have a good track record of allowing quick transition. Most importantly, thanks to our partners, IMEC is a research institute in Belgium, KTI is a research institute in Korea, and UAB is the University of Barcelona. Without these guys, some of those MTM technologies would not be possible. Okay. The last slide, the most important, Thank you.